So we're getting toward the end of the kinematics portion of the course, and it's about this time in the course when students start to get really confused. So I wanted to do a couple of other examples that I think might help. So here's the first example. So here we have a car, and we're going to call this car point B, and it's traveling around a circular track, and it's got a constant angular speed, theta dot. And we're asked to find the velocity and acceleration vectors in terms of theta, rho, this value rho that we have here, and the unit vectors of any reference frame. Okay, so first of all, before I jump in, I need to say that there are several different ways that you could work this problem. I'm going to do it using the rigid body kinematics equation from the book. I'm also going to do it using the basic kinematic equations and just the unit vectors of an inertial reference frame. You could also use polar coordinates to solve this problem. You could try to use normal tangential components, but you don't have any information about velocity. So normal tangential components are going to be tricky, but polar coordinates would work because you have information about r and theta. Okay, but anyway, I'm going to use the rigid body kinematics equations from the book. So to get started, I know that I'm going to need a rotating reference frame, right? And I need that reference frame to, I need its origin to be over here at point A. So notice that the car, its axis of rotation is not at the center of the circle as you might expect. It's over here at A. So there's my point A, and I'm going to put my unit vectors such that their origin is at point A. So here's my A1 unit vector, and A1 is always going to pass through the car. And then I need another unit vector that is perpendicular to A1, and it points in the direction of increasing theta. So this is going to be A2. A3 is going to be A1 cross A2, so it's going to be coming out of the screen. Okay, so there's my rotating reference frame. And now I need an earth fixed reference frame. And so I'm going to go ahead and put it such that its origin is also at point A. I'm just going to co-locate this point E at point A. And I'm going to define E1 and E2 such that they are equal to A1 and A2 when theta is 0. So when theta is 0, A1 would be right here. And so I'm going to go ahead and define E1 to be along that direction. And that means that E2 is going to be vertical. So E2 is going to be the direction that A2 would have when theta is 0. So here is E2. And again, E3 is E1 cross E2, so it's going to be coming out of the screen. Okay. So now I said we were going to use the rigid body kinematic equations, and you might be looking at this thinking that this is rotation about a fixed axis, but be really careful because we said that the axis of rotation is over here at A, and that means that r, the distance from A to B, is not constant, so we have to be really careful. And sometimes, just to be on the safe side, we want to start with these the equations for general planar motion plus telescoping, and then we can, as we work the problem, we can identify the values or the terms that are going to be 0, and they'll just fall out of the equation. In fact, this is rotation about a fixed axis, but with telescoping. So we have rotation about a fixed axis, we have telescoping, we don't have translation, but we still need to start with these equations. They're the most complicated, and they're going to get us the right answer in this case. Okay, so we know we're going to need these two equations, and as a result, we know that we're going to need values or terms for all of these elements. All right, so let's start there. Let's see if we can write expressions for each of those elements. And I'm going to start with the velocity of A with respect to E. Now notice that A is not moving with respect to E. It is rotating, It's rotating, but it is not moving. And so its linear velocity then must be the zero vector. It's not moving. All right, so we're off to a good start. The velocity of B with respect to A. What is that? This is a really tricky point, and I'm going to show you, I'm going to do this one. I'm actually going to come back to this, and you'll see why in a minute. So let's say we don't have enough information yet to write the velocity of B with respect to A. Okay, so let's do omega, so the angular velocity of A with respect to E. And that's just going to be theta dot, right? That's theta dot. And that is going to be it's going to be in the E3 direction, but E3 equals A3. So we can write it either as E3, theta dot E3 or theta dot A3. And we can use either unit vector, whichever one is more convenient. All right, so the next term that we're going to need is the position of B with respect to A. And hopefully you can see that this is just going to be R, so it's going to have magnitude R. It's going to have direction A1, and A1 is always going to pass through that car, point B. So the position of B with respect to A is always going to be RA1, right? And we have a little bit more information. We know that R is rho, and rho is a constant, times cosine theta. So we can just go ahead and write this as rho cosine theta A1. Okay. Now, interestingly, I think we can write an expression for the velocity of B with respect to A now, because the velocity of B with respect to A is the time derivative of the position of B with respect to A, right? But we always take derivatives with respect to respect to a specific reference frame, and in this case, the reference frame is A. Okay, that's a little unusual. It's absolutely fine though. We can take the derivative with respect to reference frame A. And to do that, I'm just going to say, I'm going to plug in this expression, rho cosine theta A1. So I'm going to take the time derivative of rho cosine theta A1 with respect to time. And since we're taking this in the in the A reference frame, don't do that. The A1 unit vector is going to be constant in that reference frame, right? Because the whole reference frame is rotating. So so we can just take this time derivative, and hopefully so rho is a constant, so hopefully you can do this by yourself. This is going to be negative rho theta dot sine theta A1. Okay, and if you didn't follow that, make sure you ask. Okay, make sure you understand why this is true. All right, so I think that's pretty good. Now I'm going to go ahead and write expressions for the acceleration terms, because I know we're going to need those. So I'm going to go down here. I'm going to start with the acceleration of A with respect to E, and again, point A is not moving with respect to E, so this is just the zero vector. The acceleration of B with respect to A, do you know what this is going to be now? Okay, this is a little bit tricky, but we just did it. So all we're going to do is we're going to say this is the derivative of the velocity of B with respect to A with respect to time, and we're going to again take that in the A reference frame. And so we can just plug in this expression for the velocity of B with respect to A that we just found. So this is going to be the derivative of negative rho theta dot, sine theta A1 dt, and we're taking this in the A reference frame. And I'm gonna run out of room. Let me just come to the next line. So this is gonna be, this is gonna have a couple terms because we're gonna have to use the product rule and the chain rule. So let me see if I can do this. This is going to be negative rho theta double dot sine theta A1 minus rho theta dot squared cosine theta A1. And again, make sure you understand how that works and why that is true. Okay? And also you should be checking my work. All right, so that's the acceleration of v with respect to A. We have omega, we have velocity of v with respect to A. Okay, so we're gonna need omega dot. We're gonna need omega dot of A with respect to E. And this is just the time derivative of theta dot E3 or theta dot A3. So this is just going to be theta double dot E3 or theta double dot A3. And I think we have everything else. So we should be ready to go. I'm going to just kind of draw a line. So yeah. So I keep everything separate. Let's do some space management. All right. So I'm going to come up here and I'm going to see what I can do with velocity. See if I can find the velocity of v with respect to E. And so I'm just going to plug in, because I don't need to change the subscripts in this case because we called the car B. So I'm just going to go ahead and plug in. So the velocity of v with respect to E, and I'm working here. So the first term is the velocity of A with respect to E, and that is just the zero vector. The velocity of B with respect to A is negative rho theta dot sine theta A1, yes. And then we've got omega, so omega of A with respect to E is going to be, it's theta dot E3 or theta dot A3, and I'm thinking ahead just a little bit. I'm going to have my R in terms of the A reference frame, and I'm going to need to take the cross product, and it's going to be more convenient if I get all of my unit vectors in the A reference frame. So I'm going to write this as theta dot A3 cross the position of B with respect to A is here, cross rho cosine theta A1, right? Okay, and then I just take the cross product, so the velocity of V with respect to E is negative rho theta dot sine theta, and then A3 cross A1 is going to be positive A2, so this is going to be plus rho theta dot cosine theta A2, and oops, I forgot, I forgot my A1, I'm sorry, let me get it in here. Directions are important, don't forget them. Sine theta A1. And that is the correct answer for the first part. Yeah? Okay. All right, so let's do acceleration, and it's not any harder, but there are more terms, so it's just a bit more cumbersome. So let's see what we can do with this. So here, we're working here with this equation, and just to save space, I'm going to go ahead and plug in terms to the extent that I can. So here's the acceleration of B with respect to E. So the acceleration of A with respect to E is the zero vector. The acceleration of B with respect to A is this, right? So this is minus, I'll go ahead and write it as separate terms. So minus rho theta double dot sine theta A1 minus rho theta dot squared cosine theta A1. And then, okay, and then I've got a cross product, and I'm going to do it on the next line. So plus 2 omega of A with respect to E, so that is theta dot A3, and I'm going to use the A unit vectors again. So theta dot A3 cross the velocity of B with respect to A, cross, and this is going to be negative rho theta dot sine theta A1, yeah? And then plus omega dot, so this is going to be theta double dot A3 cross the position of B with respect to A, which is rho cosine theta A1, rho cosine theta A1, and then plus, and this last term is kind of long, so this is going to be omega of A with respect to E, so it's going to be theta dot A3 cross, again, theta dot A3 cross, again, the position of B with respect to A, which is rho cosine theta A1. Okay. All right, so that's not too bad. I'm just going to go through now and take the cross products. So hopefully you know A3 cross A1, oof, it's going to be A2, but there's a negative sign in there. All right, so let me come down here and let's just start with the A1. So we'll do negative rho theta, I'm just writing these again, theta dot sine theta A1 minus rho theta dot squared cosine theta A1 plus, now, so I said A3 cross A1 is A2, but there's a negative, so this is negative 2 rho theta dot squared sine theta A2, I believe. Okay, and then the next one is A3 cross A1, so that's just going to be, it's A2 again. So that is going to be plus rho theta double dot cosine theta A2, and then plus here I'm gonna take this cross product right here. So A3 cross A1, so this is going to be in the A2 direction, so I'm going to write this as a rho theta dot cosine theta A2, and then we have A3 cross A2, which is going to be negative A1. So this is going to be negative, right? So negative theta dot A3 cross rho theta dot cosine theta A2, so minus rho theta dot squared cosine theta A1. Okay, and I see that I missed a dot over that first theta dot, and okay, and now there's one other thing that we can do to kind of simplify things. We can note that we were told that the angular speed theta dot was constant, so that means that theta double dot must be 0. So we can take out all of the theta double dot terms. So it's going to be just those two, and I'm going to collect terms one more time. So for A1, we're going to get -2 rho theta dot squared cosine theta A1, and then -2 rho theta dot squared sine theta A2. And then if you were given additional values, if you were asked to find the acceleration or the velocity at a specific time or under specific conditions, you could just plug in values, and this should give you the right answer. Okay, and now I'm going to do this problem using only the Earth fixed reference frame. So let me put back, so here's our point B, and here's point E, and I'm going to add my Earth fixed unit vectors. I'm going to go ahead and call these E1 and E2. You can call them whatever you like. E2. All right. Now, for this approach, I'm just going to use the basic kinematic equation. And so I'm going to start with the velocity of B with respect to E is the position of the derivative of the position of B with respect to E with respect to time. I'm going to take that in the E reference frame, but we're only working in the E reference frame, so that really goes without saying. So I just need an expression for the position vector. So hopefully we wrote before that the position of B with respect to E was just RA1, but now we don't have that A unit vector. And so we're going to have to write it in terms of the E's, the E1 and E2. And hopefully you can see that this distance right here is r cosine theta, and the vertical distance is r sine theta. So the position of B with respect to E is r cosine theta E1 plus r sine theta E2. But remember, we have a little bit more information about r. We know that it's rho cosine theta, and rho is a constant. So I'm going to rewrite this position vector in terms of rho cosine theta. So this is going to be rho cosine squared theta E1 plus rho sine theta cosine theta E2. And then I can take the time derivative. Yeah, this is not going to be easy, but we can certainly do it. So the velocity of B with respect to E. So I'm going to take the time derivative. So rho is a constant, so this is going to be 2 rho cosine theta. But remember, we have to apply the chain rule. So the derivative of the cosine of theta is negative sine theta, and we still have to apply the chain rule. So we still need that theta dot. And then this is in the E1 direction. And then for the next one, we have to apply the product rule and the chain rule. So this is going to be rho cosine squared theta, because the derivative of the sine is cosine theta dot E2. And then I'm going to take the derivative of the second of the cosine. So this is going to be negative rho sine squared theta times theta dot in the E2 direction. And now I can just kind of do the multiplication, collect terms. So for E1, I'm going to have negative 2 rho theta dot sine theta cosine theta E1. And then for E2, I'm going to have plus rho theta dot times the quantity cosine squared theta minus sine squared theta E2. And that should be the right answer. And then if you had values, if you're asked to find the value of the velocity at a specific time under specific conditions, you could just plug in values. All right, but for now, we were also asked to find the acceleration. All right, let's give this a shot. And let's just remember acceleration of v with respect to e is the time derivative of the velocity vector, right? And we're working in the e reference frame, so I'm not going to worry about specifying the reference frame. So here's the derivative. So here I'm going to start with the first term, the E1. And I'm going to need the product rule. So here we go. So -2 rho theta double dot. And I'm gonna use shorthand. So this is going to be sine theta cosine theta. And then I'm going to take the derivative of the sine. So this is going to be -2 rho theta dot cosine squared theta. Oh, and I'm going to need another theta dot. So this is going to be theta dot squared. And that is in the E1 direction still. And now I'm going to take the derivative of the cosine. So this is going to be positive 2 rho theta dot squared sine squared theta E1. Okay, so that's it for E1. That was 3 terms for E1 because we had 3 terms that were functions of time. Okay, now I'm going to roll to the next line. I'm going to do E2. So this is going to be, I'm going to start with the theta dots. This is going to be rho theta double dot cosine squared theta minus sine squared theta E2. And now I'm going to do plus rho theta dot. Okay, now this is tricky. We need to do 2 cosine theta. The derivative of cosine theta is negative sine theta. So there's negative sine theta, and then I need that theta dot. And then minus 2 sine theta. The derivative of sine theta is cosine theta, and I need the theta dot. So I think that's it. And this is in the E2 direction. So my acceleration of v with respect to e. And before I go on, I should also mention that theta dot is a constant. We're told that. So theta double dot is 0. So the theta double dot terms are going to fall out. So there's 0. Okay, so we're left with this. So here's 2 rho theta dot squared sine squared theta minus cosine squared theta in the E1 direction. And then plus rho theta dot squared. Oh, let me start over because there's a -2 that I can pull out. So minus 2 rho theta dot squared times cosine theta sine theta plus cosine theta sine theta. So let me do one more and we'll have it. Minus 4 rho theta dot squared cosine theta sine theta e2. Okay. Cumbersome, yes. Doable, also.